So to do that, we'll actually take a look here at our code just to get a sense of what's going on. It looks like we have, we have our normal updated velocities and updated locations like we've had in previous videos, accelerate the blob or any of the planetoid activities that you've done. So nothing new there. It's kind of the same idea of trying to get the particle to move, update its location. Now, then we also have this code down here. So then we have these if statements, which are talking about the target particle, basically the position of the incoming particle as well as the target particle. But we're talking about a minimum distance. Well, that minimum distance is going to be calculated here with this R statement. Notice right now we have it commented out, so we actually have to fix this. So in this instance, we're not actually going to we're not solving for R in a sense. We're not putting in some sort of, equation that's in terms of like our charges and our constants and things like that. So we're just looking for the minimum distance that would be between these two particles. So the target particle and then the incoming particle has passed it. So to do that, we're going to actually change this R, so we can uncomment this. And then we'll want to change this, and we'll put an absolute value in here just so that we keep the distance positive. Because obviously, when this thing starts, the position, the x position, so not the x target, but the x position of this particle over here ends up starting right here. So that's obviously less than the target particle. So we don't want that to be negative. So just to keep everything positive, we're going to put in the absolute value there. And so we have what looks like an electric field. And we also want to fix this as well, right? And one thing that I want to mention is that this electric field right over here, so this one down here, that's actually the electric field. It's not the one that the target particle feels from this incoming particle over here. It's the opposite. So it's the electric field that the incoming particle, this one over here, feels from the target particle. Next, you'll notice as when we ran this, we got this initial distance and this minimum distance. As the particle was coming in, it started to calculate and had all these different numbers going through it as it basically passed through the particle onto the right side of the screen. So, well, where did we get that from? So that comes from basically down here. All of this code right down here. So that's just, it's taking basically, remember before we had R commented out. So we didn't actually have any minimum distance to calculate. So now that we put that in, it runs all of this basically down here, and what that does is it basically draws out what we're seeing here and does these calculations to see, well, as this target particle, or incoming particle, comes in closer and closer and closer to the target particle, it calculates that minimum distance for us, basically. And then it also shows us what the initial distance was, which is right around, we had it around 500. So now we can move on into our electric field. Now, when we're doing this, it might be tempting for us to put in, instead of just putting in some value for our electric field, you might say, well, why don't we just put some number in there? It might also be tempting to put in just our general expression that we've always had for a electric field for a point particle. And just as a side note, whenever you're doing this, whenever we're doing the anything squared in here, we want to do use the multiplication symbol instead of the caret symbol because it likes that. And then something else just to note as well is this electric field that we have right here under this else if statement. That's just calculating. It's going to calculate basically the same electric field, the opposite magnitude if it were the opposite side all the way here rather than here, because when we're doing this, obviously you have this electric field. It has directionality, associated with it. So it's going to be emitting an electric field, say up, to the right, to the left, down, all these different angles, basically emanating just from that one position. And so all this other statement does is it tells us to calculate basically the electric field if it's on the opposite side.
So when the incoming particle is on this side, it feels a force back. This side feels a force.
Yeah. And so with that, which Blythe was just talking about, when we have the electric field on the other side, we want that to be positive, obviously, because we want the target particle basically to push our incoming particle continuously towards the right. So we want it to be in a positive direction. Well, if it's over here, we would want it to be negative, right? So we want the force to be negative. Well, we got to make the electric field negative then. Otherwise, actually, I'm just going to show you what it's going to look like if we just ran it that way. And so you get an acceleration that's incredibly huge. So we don't want that. So we'll basically change this electric field. We'll make that negative, so then it'll push it back once we play the code, obviously. So now we get that force, and it calculates that minimum distance for us, and the target or the incoming particle is pushed back by the target particle back to where it came from. So it's accelerated back the other direction because we put that negative sign in there. Then you have a force acting in the opposite direction. So Blythe pointed out a mistake that I made that hopefully you guys don't make. When we're putting in this electric field, like I said before, this is the electric field that the incoming particle feels from the target particle. So we actually want this charge to be Q target, as well as this Q down here. We don't want it to be just the charge from the incoming particle. Same thing still ends up happening. It still slows down and is accelerating in the opposite direction, but it's feeling that force from the target particle, but due to the charge of the target particle, not the charge of itself. So